I want you to picture a very specific moment. It's a moment that I think pretty much every single person in the business world has faced at least once.
Oh, I think I know where you're going with this.
You're sitting at your desk, maybe it's late, and you've got your data.
The spreadsheet of doom.
Exactly, the spreadsheet of doom. Maybe it's advertising spend, store sizes, foot traffic, whatever. You've cleaned it all up, you've put it into Excel or SPSS, and you feel great.
Yeah.
You are about to predict the future. You go to the data analysis tab, you hit run regression, and then panic.
The wall of text.
It is terrifying. The software doesn't just say do X, it spits out this massive just wall of numbers. There are tables, weird acronyms, p-values, f-stats.
It looks like Matrix code raining down. Over 30 different statistics staring back at you.
It can be completely overwhelming. It's like opening the hood of your car because you hear a funny noise, and instead of a simple light, you're looking at the entire schematic of the transmission.
Right. You just wanted to drive to the store.
And the temptation, the overwhelming temptation, is to just close the laptop, back away slowly, and guess. Or, just find the one number you recognize and ignore the rest.
But that is not what we are doing today.
No. Today, we're going to stare down that wall of numbers.
We are. We've got a great stack of notes here, and our mission is simple. We are going to decipher this thing. We're going to turn that gibberish into actual business decisions.
Without needing a PhD in math, you promise this is possible.
It is completely doable. The trick is realizing you don't need to look at every single number. That output isn't a mess. It's a diagnostic report card. It's really just answering 3 specific questions for you.
Okay, let's simplify it right off the bat. What are the 3 questions?
First, is the model actually any good? Like, does it work at all? Second, which specific levers or factors actually matter?
And the third?
And third, and this is the one people forget, how wrong are our predictions likely to be?
That sounds manageable. So our roadmap is, we'll look at model fit, the big picture. Then the ANOVA table, which I always thought sounded like a pasta dish.
The engine room.
And finally, the coefficients, the actual levers we can pull.
Precisely. By the end of this, you'll know exactly where your eyes should go.
Let's start at the top. Usually the first section is regression statistics, and the very first thing you see is just a letter. The letter R, multiple R.
The multiple correlation coefficient.
That sounds fancy. Is it the most important one?
It's actually the simplest part, but maybe not the most critical. It's just the correlation between the actual values in your data and the values your model predicted.
So it's on a scale.
From 0 to 1.
Okay, so straightforward, higher is better.
Higher is better. If it's 1.0, your model is a crystal ball. If it's 0, your model is basically a random number generator.
So R is the appetizer.
Exactly. The main course, the celebrity of the regression output, is the next line down.
R squared.
R squared, the coefficient of determination.
I feel like in every meeting involving data, someone eventually leans forward and asks, but what's the R squared?
It is the standard metric, and for good reason. It tells you the percentage of the variance in your outcome, let's say sales, that is explained by your inputs.
Let's make this concrete. We have an example from our source material. A marketing analyst is trying to predict quarterly sales.
Correct. She builds a model with 3 inputs: advertising spend, the number of retail locations, and competitor prices. She feeds those in.
She hits run, and the R squared comes back as 0.6724.
Okay, so 0.6724. First step, just turn that into a percentage. 67.24%.
Simple enough. But what does that actually mean? If I'm that analyst, what do I tell my boss?
It means that your model, using just those 3 things, explains about 2/3 of the reasons why sales go up and down.
2/3. Okay. That sounds decent. Is that good?
It is. In business analytics, an R squared between 0.5 and 0.7 is usually considered moderate to strong. You have a solid handle on the main drivers.
But I'm looking at that number and I'm thinking about the missing piece. If we explain 67%, there's still roughly 33% left over.
The so what question. That 33% is crucial. That is the unexplained variation. It's everything your model missed.
Like what, for instance?
Anything not in your spreadsheet. Maybe the economy took a dive. Maybe a competitor launched some viral campaign. Your model doesn't know about those things, so it dumps all that into the unexplained bucket.
So 67% tells me, hey, you're on the right track, but the 33% warns me, don't get cocky.
Exactly. It's a reality check. The map is not the territory.
Okay, so R squared is great, higher is better, but this leads me to a devious thought. If my boss wants a high R squared, Can't I just dump in every piece of data I have?
The kitchen sink approach.
Right, I'll add the weather, the day of the week, the CEO's favorite color.
Okay.
Won't that make my R-squared go up?
Here's the trap. Yes. Mathematically, regular R-squared always goes up when you add variables, even total nonsense.
So I can artificially inflate my score?
You can, but you are creating a monster. This is called overfitting. You're building a model that is great at explaining the past because it has memorized all the random noise, but it will be terrible at predicting the future.
So how do we stop ourselves from doing that? Is there a referee in the output?
There is. We look at the next line down, adjusted R-squared. Think of it as the lie detector.
Okay, the lie detector. How does it work?
It penalizes you for complexity. Every time you add a new variable, it asks, did this new variable actually add enough value to be worth the headache?
And if the answer is no?
If it's just noise, the adjusted R-squared goes down. It punishes you.
We have a perfect example of this in the notes, the HR turnover analysis.
Right. We have an HR analyst. She builds Model A with 3 logical variables.
Mm-hmm.
Salary, job satisfaction, and years of service.
A sensible, clean model.
Very sensible. And Model A has an R-squared of about 64.9% and an adjusted R-squared of 63.1%. They're close together.
Which is a good sign.
A very good sign. It means the model isn't full of fluff.
But then she builds Model B. She keeps the original 3 but adds 5 more variables. Commute time, age, education, you name it.
The kitchen sink.
And look what happens. The regular R-squared goes up. It jumps to 68.2%. So she might think, aha, Model B is better.
But look at the lie detector. Look at the adjusted R-squared.
It dropped. It went down to 61.0%.
And that's the verdict. Even though the raw score went up, the quality went down.
Right.
Those 5 extra variables just added noise, not insight.
So the advice here is stick with Model A.
Absolutely. We call this being parsimonious. In data science, simpler is usually better. If you can explain almost the same amount with 3 variables instead of 8, take the 3.
Okay, so we've checked R-squared and adjusted R-squared, but let's be real. If I walk into the CFO's office and say, good news, our adjusted R-squared is 0.63, she's going to look at me blankly. She deals in dollars.
A very fair point. Percentages are abstract. We need something in the units of the business. That is where the C comes in,
The SE.
the standard error of the estimate.
Okay, what is it actually measuring?
Think of the C as the average miss. It measures the typical distance that the real data falls from your prediction line.
So if I'm predicting house prices, the C is in dollars.
Exactly. Let's use the housing example from the source. Suppose you have a model and the C comes out to $18,000.
Okay, 18,000. So if my model predicts a house is worth $350,000, what does that tell me?
It tells you that while $350,000 is your best guess, you should expect the actual sale price to be roughly plus or minus $18,000 from that number.
So somewhere between $332,000 and $368,000.
Right, that's a one standard error range. About 58% of the time, the real price will fall in that band.
And what if I need to be more certain?
Then you double it. The rule of thumb is that about 95% of the time, the real value will be within 2 standard errors. So plus or minus $36,000.
I really like this because it manages expectations. Instead of promising this house will sell for $350,000, I can say we are 95% confident it will sell between $314,000 and $386,000.
Precisely. It turns a rigid prediction into a robust range, knowing the margin of error is often more valuable than the prediction itself.
Okay, moving on. We've looked at the fit, we've looked at the error, now we have to look at the section that scares people the most, the ANOVA table.
The engine room.
It looks terrifying. It has columns like sum of squares, mean squares. It feels like high school calculus coming back to haunt me.
Good news? No. You can ignore most of it. The ANOVA table is just there to break down the variation, splitting the good variation your model explains from the bad variation it doesn't.
Okay, but if I'm skimming this, where do my eyes go?
Go straight to the column marked F, the F statistic.
The F-stat. What is it testing?
It's the pass-fail test for the entire model. It asks a brutal question. Is this model completely useless?
Wow, harsh.
It tests the null hypothesis that all your inputs are worthless. Basically, it's asking, is your fancy model doing anything better than just guessing the average for everyone?
So we want a big F.
We want a big F. Think of it as a ratio of signal to noise. If F is close to 1, the signal is basically the same as the noise. Your model is trash.
In example 14.4 from our notes, the calculated F statistic is 35.15.
Which is huge. An F of 35 is extremely strong evidence. It means the likelihood of this happening by luck is basically 0.
And right next to the F-stat, there's a column called significance F.
That's the p-value for the f-test. You want that number to be tiny, usually less than 0.05. If you see 0.000 something, you're in business.
So on the ANOVA table, look for the F. If it's big and the significance is small, the model works. We can proceed.
Correct. The engine is running. Now and only now can we check the gears.
The gears being the coefficients, this is where we see the actual variables: salary, experience, education, and numbers next to them.
These are the B values, or slopes. This tells you how much your outcome changes when an input changes. This is where the specific insights live.
Let's use the salary example from the source. We have an equation. Salary equals a base plus $2,500 times years of experience plus $8,000 if you have a graduate degree.
Simple equation. But interpreting it requires a very specific phrase. If you take a stats class, they will drill this into your head.
And I see it here in bold.
You cannot interpret a coefficient without saying, holding all other variables constant.
Why are you so strict about that? Why can't I just say experience is worth $2,500?
Because that's how the math works. In the real world, variables are tangled up. People with more experience often also have more education. If you don't hold the other variables constant, you get a muddy picture.
So explain the $2,500 coefficient using that phrase.
That coefficient of $2,500 means if I take two people who have the exact same education level, same everything else, but one has one more year of experience, that person makes $2,500 more.
I see. It isolates the impact. It separates the experience effect from the education effect.
Exactly. It gives you the pure effect of that variable.
Okay, that makes sense. Pure effect. But how do I know that $2,500 number is real? Maybe it's just a fluke from the data we happen to get.
Now you're asking about statistical significance again. For that, we look at the columns next to the coefficients, the t-statistic and the p-value.
More letters. T and P, how do we read these?
The t-statistic measures precision. Here's a simple rule of thumb. If the absolute value of TID is greater than 2, the variable is likely significant.
Greater than 2. Easy to remember. And the p-value.
The p-value is the probability that this result is a fluke. It asks, if there were no relationship at all, what are the odds I would see data like this just by random luck?
So we want that probability to be low.
Very low. We generally look for a p-value less than 0.05.
So if years of experience has a p-value of 0.03.
It means there is only a 3% chance that the relationship we're seeing is due to random luck. We take those odds. We call that statistically significant.
But what if graduate degree has a p-value of 0.20?
That's a 20% chance that the result is just noise. That is way too high. Statistically, we can't say it's different from 0.
So even if the coefficient says $8,000, if the p-value is 0.2, we shouldn't trust it.
You basically treat it as 0. You shouldn't base a pay policy on it. The data is telling you, I'm not sure about this one.
So when you look at that list of coefficients, you're scanning. You look for t-stats bigger than 2, p-values smaller than 0.05. Those are your keepers.
Exactly. You're filtering the signal from the noise.
So let's bring this all together. We've gone from the sheer panic of the output window to actually understanding the story. First, we check R-squared to see if the model explains enough to be useful. Second, adjusted R-squared to make sure we aren't just stuffing it with junk.
Right.
Third, we look at the C to get a real dollar range for our predictions.
What the boss cares about.
Fourth, we glance at the F-stat to make sure the whole machine isn't broken. And finally, we check the p-values on the coefficients to see which drivers we can actually trust.
That is the complete toolkit. You can now read the diagnostic report card.
But before we wrap up, I noticed something in the key takeaways section that feels like a final warning. It's a distinction between two types of significance.
Yes. This is maybe the most important takeaway for a leader. The difference between statistical significance and practical business significance.
What does that actually mean? Because significant usually means important.
In statistics, significant just means not random. Doesn't mean big or important. It just means it's real. So imagine you run a massive regression on millions of customers. You find that changing the font color on your website from blue to dark blue increases sales. The p-value is 0.001. It is statistically significant.
So the data says do it.
Hold on. You have to look at the coefficient. The coefficient says it increases sales by 1/10 of a cent per customer per year.
Oh, it's right. Nothing.
It's real. It's not 0. But is it practically significant? Is it worth calling the web dev team, having meetings, risking a bug for 1/10 of a cent?
Probably not. The cost of the meeting is more than the profit.
Exactly. And that is where the human element comes in. The software can tell you if a number is statistically significant, Only you can decide if it's practically significant.
That is such a crucial distinction. Don't just chase the low p-values. Look at the b-value of the slope and ask, is this impact big enough to move the needle?
Exactly. Don't let the statistics override your business common sense. Use the tools. Don't let the tools use you.
I think that's the perfect place to leave it. Next time you're in Excel and you hit that run button, don't panic. Just remember, it's a report card. Check the fit, check the error, check the levers, and always ask if it actually matters.
And hey, maybe check if the CEO's favorite color is in the data set, just in case you need to delete it.
Don't give him ideas. Thanks for listening to this deep dive. Go forth and analyze.
Goodbye, everyone.